Hello, I'm Amy, and I'm here today with Dilisan, Sito, and Meghan to present the Stanley Tower by UBC Seismic. We're first going to start things off with our architectural concept, the key to which is its downtown location here in Salt Lake City. We chose to place the building adjacent to the blue and green lines, the LRT lines, which allow for easy access to nearby parks, schools, and shopping areas. This helps to reduce daily reliance on cars. And next, in this drawing we have the different levels in our building. On the orange we can see the different types of residential units present in our building. In blue we have the simple commercial space, and in purple we have public spaces that can be enjoyed by anyone. Then for our key features, one of the biggest ones that we tried to integrate throughout our structure were smart building systems that help to manage the lighting, cooling, and heating systems of the building to reduce the reliance on the coal power grid of Utah. Next, I want to highlight our art installation that we created to showcase the past and future of Salt Lake City. And we chose to install it above our facade system designed from locally sourced limestone. Then finally, I want to highlight our use of solar photochromic photovoltaic panels throughout our window system. I'm going to hand things off to Dilly.
Thanks, Amy. While a site is ideal from an architectural standpoint, we need to consider the geotechnical considerations as well. The site is located between West Valley and West Alchipalt Fault zone, and there's a 40% chance of a magnitude 7.7 or greater earthquake to occur in the next 50 years. Historically, similar earthquakes of that size have occurred in every 1,000 years, and in the past, most recently, 1,500 years ago. Local geology consists of plastic clays with interlocking layers of sand and silt. Salt Lake City is over a sediment basin which can amplify seismic waves. As well, due to the high water table and the poorly graded sand, there's a high likelihood of liquefaction up to 80 feet. Therefore, this site class is classified F. We recommend using steel pile socket up to 85 feet to the dense, strong sand to resist lateral movement.
Thank you, Dilisan. All of this informed our structural design. The striking shape created design challenges, including the greatly reduced stiffness and shear capacity of the narrow section, as well as discontinuities of the lateral system. Due to the atrium and high terrace, it was impossible to place vertically aligned columns spanning the entire height of the tower. To solve this, we have placed diagonal columns at the 9th floor in order to create a load path connecting the offset columns. Additionally, we have reinforced the diaphragm on this floor to resolve the horizontal forces. Our solution to lateral loading involves a braced core to ensure continuity of the lateral system. Eccentric bracing allows light to filter through to the atrium, while also providing access points between the inner and outer sections. External bracing helps reduce the displacement and acceleration of the roof, while an outrigger system transfers load from the core to the exterior braces, thus improving the effectiveness of our reinforcing system. This year, we also decided to look at damping devices to improve performance. Friction dampers were selected for their cost efficiency and ease of scaling. Scaled down devices used in our tower function using felt pads between two sliding members to help dissipate energy, while fasteners can be used to adjust the damper response. They are attached to the tower using twisted wires so that they can be removed for fine-tuning and calibration. On my sides, you can see that we installed the dampers between the 8th and 10th floor, and we'll expand later on our damping analysis in the presentation. Because of the high seismic risk at the site, we created scaled balsa wood models to test our design and ensure safety. This was done through a combination of analytical models and physical testing to improve our accuracy. As part of the design process, 2 balsa wood towers were made. We started with conceptual designs and member optimization in SAP 2000, before moving on to detailing the joints and constructing the first prototype tower. We tested the prototype on a shake table in order to calibrate our analysis model parameters. With refined model and observations of the physical response, we created an updated design and constructed our second and final tower. Only non-destructive testing was done on the second tower on SAP 2000 in order to calibrate our SAP 2000 model and predict the performance of the model. The analysis work includes linear time history and modal analysis, with the relevant modes to the direction of shaking shown on either side of me. Modes 1 and 2 have very similar periods due to the symmetry of the design, and mode 3 would not typically be present in an ideal structure. However, due to slight imperfections, it could induce accidental torsion. A notable issue in the tower shape is the presence of higher mode frequencies from varying stiffnesses. Once the modeling and design work was done, we began on construction. Two major considerations were construction quality and joint integrity. We wanted to use wall jigs because they have a higher accuracy and the ability to provide notch joints. However, the complexity of the structure required more consideration. We created virtual modeling and construction sequencing to aid in the construction process. And now Megan will take us through the physical testing.
Thanks, Sito. So it's impossible for us to accurately represent the complexity of real-world structures using computer analysis. However, we use physical testing to calibrate our parameters in order to run our SAP 2000 analysis. Shown here is a sine sweep test that we did after it's been Fourier transformed, so we were able to determine the modal frequencies of the physical balsa wood tower. We use these to adjust the balsa wood's elastic modulus, and we're able to get modes 1, 3, 5, and 11 to be very similar to our sine sweep results. We also note that higher modes are present at lower frequencies now, which will affect our tower's response. For our free vibration test, we induced an initial displacement and plotted the acceleration versus time of the response. Shown in the purple line, that is the shaking in the direction of motion over time. As time goes on, the response decreases before re-increasing. In the direction perpendicular, which is shown dashed, we have a similar response but out of phase. This suggests the presence of mode coupling, which is when energy transfers between modes during the shaking. Plotting the square root sum of squares of the acceleration in both directions against each other, we notice a more typical damping response. We also were able to validate our 0.23 second period from the sine sweep analysis. Earlier, we talked about how we chose to implement damping devices into our structure. When we tested our prototype tower using ground motion 2, we noticed that this transition area, shown here, has significant displacements and velocities that make it an ideal position for us to play our dampers. Damping is proportional to the velocity seen, so we tried to capitalize this in order to reduce cost and weight by adding extra dampers. We also made the dampers so that they're removable, and that way we could test the same structure iteration both with and without the damping devices. So this shown here is that same purple line from before, where it's the direction parallel to the direction of shaking, acceleration versus time without the dampers. And now overlaid is that same measurement, but with dampers added. You'll notice that the mode coupling effect has been reduced greatly, and the period between energy transfers has been increased. Now we've plotted the square root sum squares of the motion in both directions, and both with them without dampers. With dampers, we noticed a 14% increase in the damping ratio. While we didn't want to risk damaging our final structure, so we didn't do ground motion 2, we were able to do tests with the first ground motion. We noticed a very slight difference with and without the dampers. However, we anticipate a much larger impact for ground motion 2, where higher velocities will be able to engage the dampers better. We used the motion without the dampers to validate our time history results in SAP 2000 and used the analysis with the dampers to calibrate the link friction springs elements used in SAP 2000. Our final section will go over our performance predictions. The peak, roof, and displacements shown here directly feed into the cost of the structure due to seismic damage over its lifetime. The weight relates to construction costs as well as damages due to earthquake events, and the rentable floor area helps increase the annual revenue of the project. Over a design life of 300 years, we anticipate a final annual building income of $270,000. We hope that we've demonstrated that the Stanley Tower has an efficient gravity, lateral, and damping system that makes it able to withstand 50 and 300-year earthquakes. We included architectural and sustainable features that make it a leading design and an iconic landmark in Salt Lake City. Thank you for your time, and we're open for any questions.